French. We have discussed about the velocity coefficient in the last class. I mean, why we did use this velocity coefficient, and of course we have discussed some of the special cases where the pressure may not be hydrostatic in a flowing fluid. Now today we shall be taking up some problem of the real field, just to have a feeling that why we are doing all these things and where these things can find its application. Of course, we are taking a problem that is practical use of velocity coefficients in channel flow. Well, and before going to that, let us recapitulate what we did in the last class. First, we did discuss that velocity through different points of a flow cross section is not equal. What we mean by that, velocities through different points of a flow cross section is not equal. That is what we did discuss. And by that what we mean that if this is the cross section, velocity at different point will be different. Fine, that was discussed in the last class. Then, but most of our computation, say suppose we want to calculate energy of flow, or we want to calculate what is the mass flowing through a particular section, or when we want to calculate, say, what is the momentum of that flow, and different sort of calculation we do. In all those things, in all those calculations, our velocity is an important parameter. And that velocity we use always as the average velocity, because in real situation we do not find, it is not possible to have the velocity of each and every point separately, and that is not possible. So, most of the computations are done using average value of the velocity. Well, now so to take care of that in reality the velocities are different, but we are using a average velocity. So, we use some coefficients that we termed as velocity coefficient, and say one of those coefficient is energy coefficient that we use, energy coefficient alpha, that we use for calculating energy. Then another coefficient is momentum coefficient beta, which is used for calculating momentum. Well, with this discussion we can go ahead to a real problem. Say in a field, suppose in the field, in a river we want to compute energy or mass or the momentum, then what we will be basically getting from our observation in the field. In the real field we need to carry out hydrographic survey. Okay. So, by hydrographic survey what we can get, let us see. I am just explaining this in this slide. Let's say our river is this one, this is the river, and water is flowing at this level. Okay, this is the bed. Fine. Now, there are different methods of conducting field experiment or field observation. Say if we want to know what will be the, as we have seen that what will be the velocity at different point, then we can go by one procedure that, say, we can have a section from here to here. Suppose this is our the section what we have in front, that is the section, let this be the section. Okay, and in this section we have some equipment that we call as a current meter. Earlier the procedures were like this. Earlier means, why I am saying earlier, because nowadays a lot of sophisticated devices has been developed, and that way the procedures are becoming more simple. Earlier it was very much cumbersome. Say we need to decide, suppose this is the section from here to here, first we need to decide that this is our alignment, and in this alignment we need to move. Suppose we are carrying a boat and we are moving to this point, and we have equipment, suppose current meter, then putting the current meter at this point we can measure the velocity. or some other equipment also we can put, of course. So, say one equipment I am saying about this current meter, suppose we are putting the current meter and we are measuring the velocity here. Then we can put the current meter here, again we can measure the velocity. So, there will be current meter will be mounted on some vertical rod, so that, and we know the distance or depth at which we are putting the current meter and then what velocity we are measuring. Then when we are moving in this direction, then we are putting it here and here, or maybe here. So, like that at different point we are putting the current meter and we are measuring the velocity. Okay. Well, now from this record, now what sort of problem we can have when we are moving along this point? We need to keep our boat fixed here, that is one problem. Then sometimes we keep on moving, then measures, then we need to make lot of correction in those measurement, because there will be a speed of the boat also. So, anyway, by some measures we can measure the velocity at this point. Then we have observed that, okay, in this vertical section some velocity we are getting, and there may be, when we plot this thing, again on surface also we can measure velocity. That surface velocity we can measure by putting a float on the surface. That float we are putting, and we are observing that how many what distance it is moving in a given time, so that we are getting velocities. And then suppose in surface this is the velocity, at this point some amount of velocity. So, if we plot all those things, we can get a velocity vertical velocity variation in the vertical section. Similarly, here we can have another velocity diagram, here we can have another velocity diagram with different velocity, here we can have another velocity diagram, like that. Then we can have, say, average velocity of this section. We can have average velocity of this section, of a particular section. And for obtaining the average velocity, we have already discussed in the last class, that is how we can derive the average velocity. Okay. So, for that section we can have average velocity. Then what we can do, we can say find a, we can just divide the entire section into several subsection, and then what we can do, for each vertical we can find a average velocity. Here also we are finding an average velocity, here also we are finding an average velocity, and then again considering this average velocity, that is this become the velocity of the average velocity here become the velocity of this section. That means now this is becoming a, suppose, elementary section, this bigger section. Then for this velocity is becoming the velocity for this section, this velocity is becoming velocity for this section. Like that, again we have a set of velocity and area, and from that again we can find the average velocity of the entire section. We can find the average velocity of the entire section by, say, considering this velocity into area, this velocity into area, this velocity into this area, this velocity into this area, and then dividing it by entire area, dividing this by the entire area, we can find the average velocity of all the section. So, this is one way of doing, or one way of finding the average velocity. Now, based on this average velocity, we can calculate what energy, what kinetic energy is flowing through this section. Now, as we did explain already in the last class, that if we just calculate the energy based on the average velocity, here again we introduce some error, and that is why we need to know what is the value of alpha, that is the velocity coefficient of this section. But when in the practical field, when we are measuring, what we are getting is that velocity at different point we are getting. Of course, this is the procedure of measuring velocity which was done earlier. Nowadays the systems are of course changing, because we have today for location, for position where we are measuring the velocity, to know that we have equipment like global positioning system. Okay. So, when we have a GPS, then it is not necessary that we need to move in a particular direction. Say we can move in this direction, okay, and then we are suppose measuring the flow velocity at this point, then we know that where we are measuring. We have a global positioning system, so we can record our position in terms of latitude and longitude, and once we record our position in terms of latitude and longitude, then we can measure the velocity. Again, for measuring flow velocity also, we have equipment like say some sensors are there. I do not want to go into more detail of that part, but we have flow meter now. That flow meter means say digital flow meter we have, where say some sensors are there. If we put that sensor at a particular depth, or rather we need not even put it in a particular depth. Say if we put the sensor, this sensor will automatically show you at what depth this is being placed. And this principle is very simple. Say if we are putting our sensor here, then there will be a pressure of this much on the sensor, and then because of that pressure it can calibrate at what distance it is, and suppose there will be some wire which is connected to your boat may be here, and then here you are having that observation meter or record you can keep here, and so you are getting at what depth it is. And again the same time, using some other principles, this flow is coming here, so it can measure what the velocity of flow is. Like that we can move and we can measure the flow velocity. I am just giving you one example how it is done in the real field, how it can do. Say here this stick is carrying a sensor at the bottom, it is not seen here, and this wire is connected to this sensor which is being placed at the bottom, and then this is connected to this flow meter, and say we are anchoring our boat, and then we can see that if the flow is, what is the flow of this river, what is the flow velocity of this river at a particular depth. That way we can keep on measuring. This boat can be moved, and with a GPS we are recording our position, so that way we can keep on going. And similarly then you can see these are the points say where we have recorded our velocity, at different point. Now from this information we are getting some idea that where the flow velocity is how much, and from that if we take a section, suppose we can now take a section along this line, these points are there, and we can take some section along this line where we have some points there, so we can know that what are the velocity at different points. And of course nowadays more sophisticated devices are coming. This is the, I mean devices is same, that is we are having GPS, we are having say flow meter. Again we can have echo sounder. Echo sounder, what it do, because here with the sensor, the depth at which we are placing, we are getting the flow depth and we are getting the velocity at that particular depth. But along with that, if we carry a echo sounder, then from that point we can record that what is the total depth of the channel. So total depth of the channel also we can get, and then velocity in terms of depth ratio, that means what depth we are measuring the velocity and what is the total depth, with that ratio what the position, that way also we can see. Well, so combining all these things, now we can have a very sophisticated vessel also like this. So survey vessel, this sort of survey vessels are well equipped with all those devices, and then say our direction also we can just fix here. You can see that here if we have all those devices where we can record the velocity, and this sort of vessels are equipped with some compass also. So if we want that in a particular direction we want to move, we can follow the compass and we can move in that particular direction, and then there is a system that automatically the depth we can adjust that after a given time, automatically after certain time this depth are recorded. And similarly if we can have a flow meter, we can record the velocity also. And then this sort of vessels has of course limitation, like that if your channel depth is very narrow, then this sort of vessel may not be able to narrow, or I mean shallow. If your channel is shallow, then this sort of vessel may not be able to move. Then also this entire device can be put in a small boat and we can carry that for measuring the flow velocity. So that way with all this system, now we can measure velocity and we can see that how the velocity in a channel at different points are varying. Now of course let me take a typical field problem. Suppose by this measures we have measured the velocity. Well, now let this problem what it state, let us just concentrate on the slide here, that a river of average width 2 kilometer. Well, I am talking about a very large river. A river, the photographs of which I have already shown, say it is of that kind. So, a river of average width 2 kilometer is flowing with an average depth of 10 meter. Please note that in an actual river we cannot have a very specific depth of this much meter. In a man-made canal we can have, but in an actual river we cannot have a say specific depth. So, it is always we talk in terms of average depth. Then a hydrologic survey was has revealed that variation of velocity across the channel is negligible. Now, what this statement mean? Okay, that I will come later. Velocity across the channel is negligible, and the velocity variation in a vertical section can be expressed as this. Suppose u is the velocity at a particular point, or rather we can say that at a particular level in a vertical direction, then this can be expressed as 0.4 plus 0.6 into y by h. Of course, we can have different expression for this sort of velocity. This is just one I am showing, and then u is in say meter per second we are measuring. This is the velocity, and y, what this y is, it is the distance in meter from bed to a point in the section. And what this h is the flow depth in meter. H is the flow depth in meter. Well, I would like to explain these things by a diagram. Well, here itself we can draw the diagram. Say this velocity across the channel, variation of velocity across the channel is negligible. By that what we mean, this is a very wide channel, say 2 kilometer width and only 10 meter depth. I mean 10 meter depth is not small, but when we compare with a 2 kilometer width, then it is of course smaller. And then as it is a wide rectangular channel, that means we are assuming this to be rectangular. In reality it will not be exactly rectangular, but we are assuming this to be rectangular. Now, in wide rectangular channel, what we could draw earlier also, the velocity diagram or the velocity variation across the channel is negligible. Means if we are observing a particular velocity at this point, of course very near to the bed there may be some variation, but little apart from the bed when we are coming, little away from this bed when bank when we are coming, this depth or at any level, at this level if we are measuring velocity, then say velocity at every point are equal. In reality, by equal we mean that it is more or less equal, but for our computational purpose we will be considering this as equal. Of course, on the side very near to the bank it will be different, but that we are neglecting. So, not significant, that is why we are neglecting, and that is why it is negligible. There is variation, but it is negligible. Okay. But when we measure a velocity at a point here and at a point here, this will be different from the velocity of this point and that point. That is, in a vertical section there is variation of velocity, and that variation of velocity is being expressed as u is equal to 0.4 plus 0.6 y by h. Okay. Now, in this channel what y is, so u is the velocity in this particular section. If I take a very small strip, suppose say a small strip I am taking, and this depth from the bed of the channel to this particular section is say y. what y means the distance up to the section from the bed, and h is the total depth. Say this total depth is h, and let me consider this small strip as say thickness dy, and then we can say that this entire cross section, that is elementary cross section, width wise it is more, but this we can call as elementary section because its thickness is less, and this area is suppose dA, this area is dA, and width of the section let this be b, width of the section let this be b. Okay. And what we are writing, the velocity at this point, is u, velocity at this point is u. So, that is what we are talking about, what this u velocity, that is like that. And suppose we have measured this u velocity in a vertical point, in reality we have measured the velocity at different point, and then when we have plotted this velocity we are getting this sort of relation. That is, say for different depth we are putting the, we are recording the velocity, then we are putting suppose y, that is at what depth, and of course we are just reducing this by dividing it by h, that is the total depth. Total depth is of course we are giving as 10 meter, this is average, but in reality at different point it may be different. Average value is 10 we are considering. So, at every point we are putting y by h, and on this side if we put the u velocity actually which is being observed, then we are getting a relationship between u and y, and that curve, say u is equal to for y is equal to 0, you can see when y is equal to 0, that is for when we are at the bed, then your velocity is in fact not equal to 0, it is equal to 0.4 when y is equal to 0. And when we are on the surface, then say y become equal to h. So, h by h become 1, and then the velocity become 1, 0.4 plus 0.6 equal to 1. So, what I mean by putting this value and that value, we may get some point, and then when we relate this point we will be getting a line, straight line, that means we can approximate this by a straight line, because we can see that this relationship is linear, this velocity is varying linearly with y. Well, let me draw a graph here itself. Say this is the velocity, in dimension I am writing, this is the u value, okay, and then suppose here let me take a vertical section, here the velocity I am mentioning like this. And as I have explained that at the surface, when your y is equal to h, your velocity become equal to 1. Your velocity become equal to 1, you put y is equal to h, you are getting 1. And at the bed, when your y equal to 0, you put y equal to 0, you are getting u is equal to 0.4. So, your velocity is 0.4 here. So, you are getting 0.4 velocity here, and you are getting 1 velocity here. Suppose this mass is 1. And between this 0.4 velocity to 1 velocity, it will be varying linearly, because our relation is linear here, but not necessarily that it will always vary linearly, because earlier we were drawing the velocity diagram in this form, that say this is something and then we are drawing a curve. But of course, here after putting this value, suppose we have seen that points are coming like this, and this cluster is like that, very well we can approximate this as a straight line, or that is why we are considering that we are fitting a line which is taking this shape. Well, so this is how from the practical situation we are coming to a position like this. Now, with this understanding, we can go to the things that what we really need from this, what is our objective and what we need. Well, so what we want to know is that our target is that compute, what we want to compute, the discharge flowing through the section. We are measuring all those things and we need to know what is the discharge flowing through the section. This is one point. And then second, we want to know the kinetic energy of water flowing per unit time through the section. When we are talking about fluid energy, I was already explaining that we are talking in terms of per unit time. Again, when we talk that kinetic energy per unit time, per unit area, that we call as a energy flux. Now here we are not talking about energy flux, we are talking about total kinetic energy flowing through the section per unit time. Okay. Similarly, suppose we want to know the momentum of water flowing per unit time through the section. So this is, or these are our interests. Let me see how we can solve this problem. Let me keep the diagram in my front so that we all can appreciate. Say this is the expression and this is what we have already drawn, and then at any point, any section at depth y, this velocity is u, that means this segment is u, and this is dy, this distance is p. Okay. Now what is our average velocity? First, to calculate the quantity, flow, discharge or mass, if we want to calculate, then we need to know the average velocity. So let us compute first the average velocity. Okay. Well, to compute the average velocity, as we know that what will be the discharge flowing through this small section. Velocity is u and area is say dA. So u velocity into the area dA, dA means this area we are talking about, dA. That will give us the discharge, and as this is varying, we can write that integration of this over the entire area, integration of this over the entire area. This will give us the total discharge Q, total discharge Q. But of course, here we know that what is dA, that in our case dA is nothing but B into dy, which is which can be approximated as B. So B into dy, this width is suppose B, so B into dy is the area. Okay. So what we can do, this we can just, as this is uniform across the channel, it is uniform, so we can integrate it from 0 to say 0 to h, depth wise we can integrate, and then we can write u, and then dA we can write as B into dy. This is what the Q. Then what is average velocity? Say average velocity will be is equal to Q by the entire area, Q by the entire area. So what we can write, that this is equal to, area is nothing but again equal to B into h. Entire area means this B into the depth h. Okay. So B into the depth h is the area. So 1 by BH into integration of 0 to h. Then u, we can replace this as the expression already given to us, that is equal to say 0.4 plus 0.6 y by h. That expression already we have, and B dy. Of course, B being constant, we can just cancel this B and this B, bringing it out. So this we can write at integration of 0 to h, 1 by h integration of 0 to h, 0.4 plus 0.6 y by h into dy. Fine. And now this problem becomes simple integration problem, and we can write it as 1 by h, then 0.4 dy integration of this we can write as 0.4 y plus say 0.6 y square by 2, and already this h is there with us, and this is from 0 to h. So, we have integrated that. Then putting the limit, we can write that 1 by h, then it becomes 0.4 h plus this also become say 0.3, and then it is y square will become a square. So, it is h. Okay. Then this, okay, let me write in this table itself, in this slide itself. So, this we can write as this h and h getting cancelled, this is equal to 0.4 plus 0.3, this is equal to 0.7. Now, see average velocity we are getting as 7, okay, 0.7 we are getting as 0.7 meter per second, 0.7 meter per second. But of course, as this in this case we are considering, I have just shown how in a systematic way through integration process considering the flow velocity in an elementary area, finally we can get the velocity. But here as the velocity is varying linearly, we can straightway also in fact find this value. Say here the velocity is 1, already this was discussed that here the velocity is 1, because when y is equal to h, this value become 1 from this equation that u is equal to 0.4 plus 0.6 y by h. So, from this we can have that. Okay. So, here it is 1, and here when y become 0, it become 0.4. So, average velocity, it is a regular shape. So, we can find out what will be the average velocity. It will be 1 plus 0.4. So, maximum is 1 plus say 0.4 divided by 2, this is equal to 0.7. So, that way also we can straightway find. But why I have done this part? Just to understand what is the how we can do it by this procedure, and of course, as it is simple we can do it, but if there are discrete value we cannot do it this way, and if the variation of velocity is not straight, suppose variation of velocity is different, is parabolic or some other shape it is taking, then we cannot do in this straight way. So, we need to go for integration. So, that way we need to see. Well, after knowing the average velocity, we can find out discharge. So, we can find out that discharge is equal to say average velocity multiplied by the sectional area. So, that average velocity already we have got 0.7, and sectional area, as we know that average width we are considering this to be 2 kilometer. So, it is 2000 meter, and then depth is 10 meter. So, we can find this to be say 14,000 cumac, 14,000 cumac. And once we get the discharge, if we need to calculate mass, here just we need to multiply it by rho to get the mass. Okay. Now, let us see that our first part is over, that how to calculate the discharge. Then the next question is to find out the energy. We need to compute what the energy can be. Now, for that we need to calculate again energy. Suppose, well, if this is the discharge, then we can in a sense we can calculate directly like that kinetic energy I am talking about. Say kinetic energy, if I calculate like this, kinetic energy is equal to half into mass into say velocity square, half mv square. Now, this v is I am talking about average velocity, what we have got already 0.7. So, this mass is nothing but half of rho into the q value, rho into q into say v average square. Now, if we calculate the energy straight way like this, it will not be correct. it will not be correct. The reason is that already we know, because the velocity is varying, we need to multiply it by alpha. So, our correct kinetic energy will be this multiplied by alpha. Now, our problem is to find out this alpha. Similarly, if we calculate momentum, momentum also we can calculate, say, mass into velocity, average velocity, but in reality this will not be correct. So, we need to multiply it by the coefficient of beta. So, we can write beta mass is equal to again rho into q into V average. So, that way we can have this mass and velocity, and multiplied by the beta we can calculate momentum. Well, now let us see how we can calculate this alpha value from the given information. Okay. So, we are now discussing about calculation of velocity coefficient. Well, velocity coefficient alpha, we already have discussed this expression. You can recall what we did discuss in the last class, that we can write as, say, 1 by a into integration of v, or here we are using the term u by, say, v average, u by v average whole cube, and this integration is over the entire area. Now, in this case again coming to the same point, as the variation of velocity across the section is negligible, we are considering this as, say, b, area is nothing but 1 by b into y, then we are considering u cube, and this v average means already we have, say, 0.7 cube. dA we can write as b into dy, and then when we are expressing it like that, we need to integrate it from 0 to h. Well, so we can write the expression as, this is not y, this is the total depth, this is the total depth, b into h. So, we can write this as 1 by h, this b and this b would get cancelled as it is constant. So, 1 by h into integration of 0 to h, then this 0.7 cube that we can bring out, say, 1 by 0.7 cube, that is the velocity, average velocity cube that we are bringing here. And then u we can write as, with this using this equation, 0.4 plus 0.6 into y by h, this whole cube into dy, Well, so this, if we simplify this 1 by 0.7, after this your problem is just simple integration and arithmetic calculation. So, let me express this as 0 to h, then just a plus b whole cube formula all of you know from your childhood. So, you can just express it as 0.4 cube a cube plus, say, 0.6 into y by h. Let me write it like that, this cube and then this cube, a cube plus b cube plus, say, thrice into 0.4 square into 0.6 into y by h plus thrice ab square 0.4 into 0.6 square into y by h square. So, this is how we can express this and dy. Okay. This is dy. Now, it is a straight way we can do the integration. Let me keep it like that, and then 1 by h. In fact, this can be written directly, because you see when you bring here, it will become, say, 0.4 cube into y. plus, and then when you put the limit this will become h, and everywhere this will become h, and h we can in fact cancel. So, this is 0.6 cube and this will become y to the power 4 by 4 and h cube. So, ultimately this when we put the limit this also become h, just then plus say 3 into 0.4 whole square into 0.6 into this will become y square by 2 and then h plus say 3 into 0.4 into 0.6 square, then it become y cube by, sorry, this is square, so it will become y cube by 3 into h. So, that way we can put, and we can put the limit from 0 to h. And when you put the limit from 0 to h, then well in this sheet itself I can make the correction that, or okay, let me write one more step. Now, let me write it here, it will be better. Well, this can be written as say 1 by 0.7 cube, then 1 by h, and then it will become 0.4 cube h plus other factors will be there, and then this term will become h again, say h to the power 4 divided by h cube. So, everywhere in fact this h, this term will become h, everywhere this term will become h when we put the limit h here, and then we can just put the value directly, and so let me just cancel this one, and this h we can cancel with this h here. This h can be cancelled with this h, then just numerical value we need to put 0.6 cube by 4 here plus say 3 into 0.4 square into 0.6 by 2 plus this is say 3 into 0.4 into 0.6 square by 3. So, when we put all this value, this h everywhere actually one h was there, and this h we can cancel with this h, and putting this value we can just calculate the value of alpha. Now, everything is known, that is only the digital value are there, and this value is equal to, we can put 1.18. This calculation if we do, this value become 1.18. So, our alpha is equal to 1.18. Similarly, for beta also we can calculate in the similar way, and then we know that beta, now I am coming straight away, say beta is equal to, we can express say 1 by h directly, say we are writing 0 to h, then here u square by v average square into dy, that we can write directly in this form. And here again if we put the value of u and other things, say it is 1 by 0.7 whole square v average square, and it is 1 by h, and then inside it is becoming say integration of 0 to h 0.4 plus 0.6 y by h whole square into dy, and from this again this part we can express in the form of say a square a plus b whole square. So, we can just break it, then we can do integration, we can put the limit from 0 to h, and then again this h and that h will get cancelled, and finally we can get the value of beta as equal to 1.06. So, what we have seen that alpha value is 1.18 and 1.18 and beta value is equal to 1.06. So, that we discussed in our last class, that alpha is greater than beta is greater than 1, that we have seen in actual calculation. So now what we mean that if we calculate our, if we go to our last slide, if we go to our earlier slide, that if we calculate this kinetic energy by simply using this formula, then it will not be completed. Rather, it will be less by 1.18 time. Actually, our alpha value is, so if we just forget about this term, then it will be less. So our actual alpha value or actual kinetic energy value will be this multiplied by alpha, means we need to multiply it by 1.18. Similarly, beta value will be, say this will be 1.06, and then it is rho, q, and then v average. So that way we can calculate momentum. That way we can calculate momentum. Alpha, in place of this alpha, we need to multiply this by 1.18 into this part. Okay. Well, so we have seen how from the practical field we can acquire data, and then using those data how we can derive this sort of coefficient, that is velocity coefficients, and then how these velocity coefficients help us in getting the computed value of momentum corrected, okay, so or energy corrected. So that way, let me take another example. This is one situation I have shown. Suppose the same river I am considering, you can just concentrate on the slide, that say velocity coefficient in a river during high flood period. Well, means suppose let me consider a river, the same river, suppose like this, as we did consider earlier, and it has a flood plain in this form, and suppose we were talking about a river of this kind, and where we could see, suppose the flow depth when it is up to this much, then say we could compute, say depth is 10 meter as we did consider here, and then this width we did consider as suppose 2000 meter, 2 kilometer, very wide river, okay, because we are considering intentionally a wide river so that we can consider this to be a rectangular one. Well, now up to this much we can do in the way what we have already discussed. Now say during flood time, that means if the water exceed this bank, during flood time water level will be exceeding this bank level, and then flood will be spreading into the flood plain. So this is flood plain, okay, these are flood plain, and water will be spreading to this level. So to prevent the flood, many a time what we do, we put some embankment here. Suppose the embankment is at a distance of 200 meter from the bank, and there also we are putting some embankment, let this be also at 200 meter from the bank. Of course, my diagram is not proportionate because you can see that here it is 2000 I am writing and this distance is 200, but anyway let us consider this as 200. Then what will happen when water is moving above the flood plain, suppose it has come up to this much height, then we will be getting the water level in this form, okay. So whatever velocity coefficient we calculated for the river during the period when there were no overflooding, that will not be valid now because the situation has completely changed. And say flow depth, now we can consider here to be say 12 meter, let this be 2 meter, water level has risen up to 2 meter from this bank level, and so this is 12 meter. And one thing we must appreciate at this point, that this section we can now consider as 3 distinct parts. Suppose one is, let me consider this as again rectangular, suppose approximating this as rectangular, say this is one. Of course, we can always consider this to be a trapezoidal also, there is no harm, but our calculation will be a little more complicated. So let me consider this as a rectangular like this, and this is one portion, this is suppose the part 1, and then this part I am considering as part 2, and this part I am considering as part 3. Well, now as the depth of flow here will be very less, as compared to the depth of flow here, because here only it is 2 meter. So, the flow velocity here will be significantly less than the flow velocity of this part. Okay. We are considering symmetrical, that means this side also same, say this side also same, and this is different. Well, suppose we got the average flow velocity of this section as 0.7. Okay, let me again consider this average flow velocity as 0.7. Suppose V of this section 2 is say 0.7. Of course, it will be a little different, but for just calculation purpose I am considering this as 0.7. And then velocity of the flow here will be very less. Say we are considering the flow velocity here to be say V1 is equal to 0.4. Okay, and here we are considering the V1 to be equal to 0.4. V3 also equal to say 0.4 we are considering. Okay, and this sectional area say we are considering as A1. A1 is the sectional area, this one. A2 is the sectional area, this portion, entire sectional area I am talking about, and A3 is the sectional area of this portion. Well, just like integration, now of course with approximating these area and approximating that this velocity, average velocity what I am giving as V2 here. V2 means actually we are talking about the average velocity. V1 also we are talking about the average velocity of this portion. Now we are just making one assumption that in this portion that is say area A1, this average velocity is 0.4, and we are assuming that variation of velocity within this section in vertical as well as horizontal in the entire cross section is not that much, and we are considering that this is the so I mean individual velocity coefficient for this area is not that much important or not that much that is not required to that extent. So, we are considering that velocity here we can consider as V1 0.4, which is say velocity which represent the velocity at all point here. Okay. Then V2 is the velocity suppose which is representing velocity at all point. V3 is the velocity which is representing the velocity in this entire section. Well, now if we then go to the alpha value, okay, if we then go to the alpha value, well, now we know the alpha, that velocity coefficient expression we can write as say 1 by A, not I mean I am writing the conventional expression 1 by A, then say when we integrate it over the area we can write that average velocity V through a small section, then we were writing V average, and then we were writing this as say dA. Well, this is the expression what we have already used. Now, when we have distinct part, this we can write in the form of summation also. How we can do this? Say 1 by A. Now, this small v what we were writing earlier for a, you can just refer to the slide, this small v what we were writing earlier for a small area, now that we can write for a small section, say section 1 there is one velocity, section 2 there is one velocity, section 3 there is one velocity. So, what we are writing this is, and V average means the average velocity, V average means the average velocity of all these sections. So, what we can do, say we can write a summation of this V, I can write as Vi, means for each section, and then this delta A, this delta A now for me is a individual section, means say section 1, section 2, section 3, like that. So, Vi cube Ai, and here I can write say V average, here I can write V average, or well, let me use a different symbol Vm, say mean velocity. Well, now already we know that okay, here I is in this problem, I is varying from say I equal to 1, 2 and 3, and of course in general if we have several of this section, this sort of section we call as a compound section. This sort of section we call as a compound section, and there can be say several sections up to n number we can go. Well, now let me just write this in a more simpler form like that. What is our total area? Total area we know very well now, it is not a problem. Say total area A is equal to A1 plus A2 plus A3. Well, and then what is our mean velocity? What is our mean velocity? If we just go back to this slide, then what is the discharge flowing through this section 1? If area is A1, velocity is V1, then the discharge flowing through this section is A1 into V1. Okay, and that way discharge flowing through section will be A2 into V2, and similarly discharge flowing through section 3 will be A3 and V3. And so average velocity we can write as say A1 into V1 plus, that is discharge flowing through this section, A2 into V2 plus A3 into V3. In fact, in reality what we are doing, this is Q1 plus Q2 plus Q3, this is the total discharge we are getting, and divided by the area, say A1 plus A2 plus A3 means the total area. So this is what the expression for our velocity. So when we talk about now alpha, what we can write, that we can see that alpha now we can write as 1 by area means 1 by A1 plus A2 plus A3. This is the total area. Then we had that V1 cube A1, V2 cube A1, those things you can write, say V1 cube A1 plus V2 cube A2 plus V3 cube A3, right. And then we have mean velocity here, and mean velocity as we know that we can write is A1 V1 plus A2 V2 plus A3 V3 divided by A1 plus A2 plus A3, and we know that this is whole cube, this is whole cube. So this is what the expression for alpha, we can simplify it into the form that V1 cube A1 plus V2 cube A2 plus V3 cube A3, and then there is one total area, here is total area cube. So if we just cancel this one, we will be getting A1 plus A2 plus A3 whole square, this cube, and this will get cancelled one, and here we will be having say A1 V1 plus A2 V2 plus A3 V3 whole cube. Well, so that way our expression becomes simple, and now we can compute the value like that. Say this is equal to, we already considered that velocity in the section 1 is 0.4, so it is 0.4 cube, and then sectional area, that width we just consider as 200 or 100 meter, what we did consider, let me see, let me write, okay, suppose this is 100 meter, let me consider this as 100 meter, then it will become more simple. Okay, say this is 100 meter, so depth is 200, so depth is 2 meter, so the sectional area will be 200, then plus say 0.7, this is the average velocity of the section 2 into, and that area is of course we are considering the 2000 meter width and depth is 12 meter, so it will be 24,000 plus then 0.4 is again this one, and we will be having 200. So this part is there, and then what is the total area? Total area is say we are getting 200 plus 24,000 plus 200, so it will be say 24,400, it will be 24,400. This is total area square, we will have to multiply total area square. So that way we are getting this total area square, and then here we are writing 0.4 into 200 plus that is what this area into velocity A1 V1, 0.7 into 24,000 plus say 0.4 into 200 again, and that is cube. So, that is what our alpha is. Then alpha value, if we just simplify this part, then we get a value of 1.00775. Okay. Like that, we can also calculate for beta. We can also calculate for beta, and you can see that this sort of situation, that means what I want to emphasize, that when we calculate a value of alpha for a particular channel section, and if we use the same alpha when it is in flooding condition or maybe when it is in very lean period, so these two should not be same, it will be different. So, we should be careful in using this value. We should know what the practical significance is. Well, now I would like to concentrate on this. I would like to draw your attention to this value. When we are talking about this alpha, why we are using this is because it is the average velocity is not equal. I mean, velocity is different in a section, velocity is different in a section, and then we are considering the average velocity, then we are computing energy, and say then we are computing momentum. So, we are using alpha and we are using beta. Now, in the calculation of average velocity itself, whether we need any coefficient, that means suppose using the average velocity we are calculating say discharge, Q is equal to average velocity into area. Now, this discharge, now say when we are, or suppose when we talk about mass, say mass, if we talk about mass, mass will be equal to rho into V average into area. Okay. Now, for calculation of energy we are using a coefficient alpha, calculation of momentum we are using a coefficient beta. Now, for calculation of mass, do we need any coefficient here? We do not, because the very basic value of V average that we are calculating, that is here itself we are considering the variation of velocity, and we are dividing it by the total discharge we are considering. Through area we are calculating individual discharge, we are summing up the total discharge, then we are dividing it by the total cross sectional area. So, here we do not require that. Then again another point I want to say, that say energy coefficient alpha we are calculating, what energy we are talking about? That we are talking about the kinetic energy. Now, if we say that energy, there are different type, or say in the total energy we have three distinct part. One is say kinetic energy, one is say potential energy, then energy due to each elevation, that is also there, and pressure energy is there. I mean potential energy and energy due to elevation, the same thing. Then we have that say pressure energy. So, all these different energy are there. Suppose we are calculating total energy. Now, in the calculation of total energy there will be a pressure energy also. Now, do we need a alpha value for calculating that energy? Say pressure energy we are calculating some amount pressure energy, and do we need any coefficient there, alpha or say some other coefficient? Yeah, definitely not. The reason is that when we are calculating pressure energy, or when we are talking about the potential energy Z, in this case our velocity is not coming into picture. Velocity is coming into picture only when we are talking about the kinetic energy, only when we are talking about the kinetic energy, and that is why this value of alpha is coming only when we are talking about kinetic energy. In this case it is not there, that is why this sort of coefficients are not coming. Well, with this introduction to the practical use of these coefficients, we could understand that how we should be careful in considering these coefficients, and of course, we have seen that we are using this for calculating mass, we are using this for calculating momentum and energy. Now, these momentum and energy are very important topic basically in open channel hydraulics, and So, based on some of the principle like the very fundamental principle of physics like momentum and energy conservation, we derive some equation, and those equations are very much useful for our computational hydraulics also. So, about all those things we will be discussing in the next class, and with that let us hope that with the very basic understanding of this topic we will be able to grasp the discussion of our next class in a much better way. Thank you very much.